Hi everyone, now we're going to talk a little bit about how to write the chemical equations for these reactions that contain species that are dissolved in water, or aqueous species, and specifically how to differentiate between those that are strong electrolytes, weak electrolytes, and non-electrolytes. So let's take a look at this example equation. Silver nitrate plus sodium chloride reacting to form silver chloride and sodium nitrate. Now, if you go to your solubility rules, you'll find that silver chloride is an insoluble salt, so we would put an S here, and everybody else is aqueous. When we write the equation like this is what we refer to as a molecular equation, which just means that we write everything out and balance them as we would any equation. Well, as you remember, when we have ionic compounds or salts like these and we dissolve them and they're soluble, they don't really stay together. In fact, I just want to remind you that for an ionic compound like sodium chloride, if you were to mix it with water when it dissolves, each ion individually is separated from each other and then they get surrounded by water particles. And when we write the equation, it shouldn't be written as NaCl aqueous, but it should be written as Na plus aqueous and Cl minus aqueous. So now, if we come back to the reaction that we were looking at earlier, we notice that several of these ionic compounds are in aqueous state. And so as a result, the reality is that they exist as separated ions. So what we have to do is write them as those separated ions. So we would take silver nitrate and break it apart into silver ion and nitrate ion. So Ag plus aqueous and nitrate aqueous. Sodium chloride would be written as Na plus aqueous and Cl minus aqueous. AgCl is a solid, so that stays together, that doesn't get separated. NaNO3 is aqueous as well, so we're going to separate that out as well. This is what we refer to as the complete ionic equations, where we take everything that's aqueous and we separate them into ions. When you write your complete ionic equation, you only separate those compounds that are in the aqueous phase and only the ionic compounds. You don't separate the solid, liquid, or gas compounds. So once we separate them out in the complete ionic equation, what you notice is that there are certain things that are identical on both sides of the equation. So for example, nitrate ion, it's on the reactant side and it's also on the product side. Another one is the sodium ion. So they're highlighted right here. Now, when something appears on both sides of the equation and they look exactly the same before and after the reaction, that means that nothing happens to them during this reaction. They are what we call spectator ions. So they don't really participate in the reaction. If these are spectator ions, what we can do is we can remove them from the reaction because they're really not an important or critical part of the reaction. So what we can do is cancel these out. So cross out the NO3 on both sides and cross out the sodium on both sides. All that's left is going to be Ag plus Cl minus on the reactant side and then AgCl on the product side, which is this equation right here. This is what we refer to as the net ionic equation, which is the ionic equation where you have removed your spectator ions. Anytime you have a reaction where you have aqueous ionic compounds that are soluble, you can write it in these three different forms. The molecular equation, which looks like this, the complete ionic equation, which looks like this, and the net ionic equation, which looks like this. Which species should we write as separated and which one should we write as together? Well, we just said that anything that's aqueous ionic compound should be separated, right? But there's a little bit of a fine point about this, and this is highlighted in this portion right here. Anything that is a strong electrolyte should be written in the ionized form, meaning that they have to be separated. So a soluble salt, based on your solubility rules, would be written as separated ions. So here's an example. Iron 2 chloride should be written as iron 2 aqueous and chloride aqueous. And since there's 2 chloride, we would write it as this. A strong acid. HCl is an example of a strong acid, so we would write it as H plus and Cl minus. Now, I will tell you in a second what is considered a strong acid and what's considered a weak acid, but right now, just keep that in mind that a strong acid is a strong electrolyte, so we have to write it as separated ions. Strong bases are also considered strong electrolytes, so we're also going to write them as separated ions. So NaOH would be written as Na plus aqueous and OH minus aqueous. The weak electrolytes and the non-electrolytes are written as a molecular form, which just means that they don't get separated. Weak acids like HCN, you never write this as H plus and CN minus, you would just write it as HCN aqueous. If you have a weak soluble base, such as NH3, would be written as NH3 aqueous. So compounds that are considered insoluble salts, you don't separate them. You write them together, just like we did earlier with the silver chloride. It's written as AgCl with a solid next to it, not Ag plus and Cl minus. Lastly, covalent molecules that are not acids or base, they are also written as their molecular form. So CO2 gas, H2O liquid, okay? So I just mentioned to you things that are called strong acids, strong bases, and weak acid and weak bases. So I want to point out exactly what these are. This is something we'll discuss a lot more in future videos, but right now I just want you to memorize them. So a strong acid is an acid that dissociates completely when we put in water. So in other words, when you put HCl in water, you never see the species HCl. What you see is the H plus and the Cl minus. A weak acid, on the other hand, is an acid where when you put them in water, they don't break apart. You see very few of the ions. You see mostly the molecular form or the HF form. Strong bases is similar to strong acids in the sense that when you put them in water, they break apart completely. So you see only the ions form, and weak bases stay together as that form. They don't separate out. The only weak base I want you to remember in this class is really this weak base right here, which is called NH3, and the name for it is ammonia. Now, how do you know whether an acid is strong or weak? Well, at this point, you have to memorize them. The easy way is to memorize the strong acids, and then anything that is not part of the strong acids would be considered a weak acid. So the strong acids that are listed here are these 6: HNO3, HClO4, HBr, HI, HCl, and H2SO4. All of these are aqueous acids that are strong. If you're given any other acid, those are all weak. So these are some examples of the weak acids. With bases, sort of similar. The strong bases you have to memorize, and those are hydroxide salts that are soluble. You can look up the solubility rules. They're going to be all the group 1 hydroxides, and then these 3 from group 2, strontium, barium, and calcium hydroxides. The weak base, as I said earlier, in this class, I just need you to remember NH3, ammonia, as your weak base.
So let me show you an example of how to complete a question where you have to write all the different form of the equation. In this case, the molecular, the complete ionic, and the net ionic equation. So I'm going to pick one of these here, iron 2 chloride and cesium hydroxide. So the first thing is you write what the reactants are. So iron 2 chloride would be FeCl2, and then cesium hydroxide would be CsOH. And the reason I know how to write this formula is basically from my nomenclature knowledge. And the products would be a double displacement product. So I'm going to swap and put the Fe with the OH and then put the CS with the Cl. So CsCl and FeOH. Now, next thing I have to remember is the charges. So Cs, if you look up the periodic table, is a group 1. So it has a charge of +1. Chloride is a -1. So that means that formula is correct. So we don't need to add any subscript. Fe in the original compound is iron 2, so it has a charge of +2. Hydroxide is a -1 polyatomic ion. So in this case, to make this formula correct, I'm going to have 2 hydroxide. We put parentheses and put 2 right here. That's my formula. Now I need to figure out what kind of state it has. Since this is a double displacement reaction and it's not acid-base, the reason I know it's not acid-base is because an acid would have had an H at one of the reactants and we don't see that. I'm going to need to go to my solubility rules to figure out what is the state of each of these products. So here's my solubility rules on the left. I can see that CS is a group 1 salt. So if it's group 1, that means that it will be soluble. So AQ. FeOH2, I'm going to scroll down here to find either Fe or OH, and I notice there's an OH OH here at the bottom. It's always insoluble with some exception, which are these guys, but iron is not one of the exceptions, so in this case that will be a solid. So that's my molecular equation. Now one thing I need to do is make sure that I balance my equation after I write the molecular equation by adding 2 to the CsCl and 2 to the CsOH. So now I'm ready to do my complete ionic equation. I'm just going to take anything that's aqueous and separate them out into ions, and then keep everything else together. So I have FeCl2 aqueous. I'm going to write Fe2 plus aqueous and 2Cl minus aqueous. I have CsOH aqueous. I have 2 in the front as the coefficient, so that means I have 2 Cs plus and 2 OH minus, both aqueous. I have 2 CsCl aqueous, so that's 2 Cs plus aqueous and 2 Cl minus aqueous. And lastly, I have FeOH2, which is a solid. So what I have there is my complete ionic equation. At this point, what I need to do is highlight my spectator ions and cancel them out. So I can see that Cl minus exists in both sides of the equation, and it's the same number, so I'm going to cancel those out. Cesium also exists in both sides of the equation, so I'm going to cancel that out as well. That leaves me with my net ionic equation, which is just Fe2 plus aqueous plus 2OH minus aqueous forming FeOH2 solid.